Hello everyone. So welcome to this course of electric vehicles and renewable energy. So far we have seen the basics of lithium-ion cell, what is the cell, how is it made, and then we went on to making the battery packs. So we know now how to make packs from cells, and we have seen a few design considerations which we have to take into account while making the battery packs. Now let's move on to cell testing and characterizations. So this is a very important step or process before we start making the battery packs. So let's see how a typical datasheet of a cell looks like, because before we start the topic of cell testing and characterizations, we should know why actually we are going to do this. So let's see what a datasheet looks like or what the manufacturer gives you. So whenever you get the datasheet, you will have few things mentioned in that. One is the basic characteristics. So for any cell, the manufacturer will specify you what is the nominal capacity. So this is for like 2600 mAh. Then nominal voltage. For this, its specific chemistry is 3.7 volts. Then the internal impedance or the resistance, which is of 70 milliohms here. And then other parameters like what is the minimum discharge cutoff voltage, which is 3 volts in this case, and then standard charging current, then what is the fast charging current, then next what is the rapid discharge current, what is standard discharge current. So what it means by these parameters is these are the nominal characteristics of the cell. You should never exceed these limits. If you go beyond these limits, then the cell warranty or the performance may not match, or the manufacturer will not guarantee anything beyond these limits. Then next it will have the mechanical dimensions of the cell. So this particular is 18650 cell chemistry. Then next are the electrical performance. So this performance, so this is a bit in detail what they tell you about the cell. So when we say nominal voltage is 3.7 volts, it does not mean that cell is always at 3.7 volts. What it means that the cell for most of the time during the charging or discharging is at 3.7 volts. So nominal voltage is 3.7. And the discharge performance. So here when the manufacturer tells you the discharge capacity is 2600 mAh, it means a standard discharge has been followed. So next parameter is the cycle life. So cycle life tells you how many cycles the cell will give you when operated at certain conditions of charge and discharge. So this particular cell gives you about 299 cycles at 100% DOD, and the charge and discharge currents are 1.3 amperes, which means it is 0.5 C, and then they say that after 299 cycles this cell capacity will come down to 80% of its initial capacity, which is the end of life. So it says you that after these many cycles the cell will no longer be used in your electric vehicle applications. The next is storage test. The storage test is very important because if you see most of the times your vehicle is in parking state. You do not drive your vehicle all the time. You charge it, you drive it, and then it is in parking stage. It is said that about 90% of times the vehicle is in parking state. So it does not mean that when you are not using your vehicle the battery does not degrade. So battery degrades all the time. So this storage performance, what they specify is for 3 months. So if you keep the cell for 3 months at certain state of charge, how much capacity will deteriorate. So this is that parameter. So they have given it for ambient of 25 degrees Celsius and at some particular SOC. So this is what you get for a cell from manufacturer, what datasheet specifies you. Next, let's see what are the important parameters which are not found in datasheet. The first and very important one, the life cycle variations with charge rate, discharge rate, DOD and temperature. We all know that the life cycles of a battery pack are impacted by how fast you charge it. So faster charge would mean higher degradation, then discharge rate, how fast are you discharging the cell, then the depth of discharge. So how much of the battery capacity are you using every time. And then the most important parameter, temperature. What is the ambient temperature, and also the cell internal temperature. Next, peak charge and discharge power. So this is very important because for short duration charging, for pulse charging and all, you will need to know what is the peak current I can pass to the battery. So this is mostly important in your regenerative charging. And during discharging, when you want high power for very short time, you need to know what is that peak current you can draw from the battery. Then next is the peak deliverable current at different temperature. This same as what we talked about, peak discharge power. The other important point is you cannot draw same amount of current from a cell at all temperatures or at all state of charges. Suppose at 80% state of charge and 25 degrees you are drawing some amount of current, then that amount of current will change based on temperature as well as state of charge. So these all things will not be told you in the data sheet. So these are the experiments which need to be performed by individual at lab level based on his requirements for what he is going to make the battery pack. The next is the internal resistance variation with state of charge and temperature. So if you see you have seen the data sheet. So it says the internal impedance or resistance to be 70 milliohms, okay, but in actual the resistance is a function of state of charge as well as temperature. The cell at higher temperatures will give lower resistance, whereas at lower temperatures will have higher resistance. Similarly with state of charge, when the cell is at lower state of charge, the resistance is higher, and with increasing state of charge up to 80% SOC, the resistance gradually decreases. So these informations are not provided by the manufacturer. Then next are material properties. So these are mostly required when you want to model the cell from electrochemical point of view. So material properties consist of what is the anode material, what is cathode material, then what are the proportions of the chemicals used, the additives, the electrolyte. So these are trade secrets and no manufacturer will share this with you. So when we want to know all these parameters, we need to do the testing at our own level. Now let's see what are the different types of tests. First is the cell performance. So cell performance are basic level tests which one must know before they start using the cell. So these tests are not very high duration, which don't take much time, and you can do it in a day or two, and time depends on the type of test you perform. The first is the capacity test. So this test is used to know what is the capacity of the cell. Then cycling at different C rates. So this test will tell you how the cell's voltage or the cell's voltage profile will be at different C rates. And then pulse test. In pulse test we subject the cell to different pulses of charging current or pulses of discharging current. Next the EIS, so this stands for electrochemical impedance spectroscopy. So this test we study the response of the cell for different frequencies. Then is the drive cycle test. So there are many different drive cycles which we have already studied, the IDC drive cycles, other things. So we will see that how the cell behaves for the particular drive cycle. Does the cell give all the required currents and power mentioned in the drive cycle. Next is the aging test. So these are the tests which take huge amount of time to do this test. The first is the cycle life test. So this test is performed to know how many cycles the cell can give. And next is the calendar aging test. So calendar aging test, as we already saw, is to see how much degradation will happen when the cell is just kept at a place. The next are safety aspects. So here we do the vibration test. So these tests we already seen in the battery pack design module. the vibration test, the short circuit test, overcharging test, the impact test, penetration or the nail penetration test, and drop test. So these tests take care of the safety aspects of battery pack, because the most important thing for a battery pack is that it should be safe. So these are very important tests. And the last are the thermal test. So this consists of temperature cycling, which means cycling the cell at different ambient temperatures. Then high temperature endurance. We all know that lithium ion cells, when subjected to higher temperatures, can lead to thermal runaway. So this test ensures that what is the maximum ambient temperature at which the cell can be cycled at a particular C rate, so that there is no risk of fire or thermal runaway. And fire test, in which cells are actually subjected to fire. Then thermal runaway propagation. So thermal runaway is a very important topic, in which so this is very important to know how thermal runaway will propagate from one cell to another. So this has to be studied. So a test will be done on that part. And the rapid charge discharge test. So this is again, when I say rapid charge discharge, this would mean higher currents. Higher current would mean higher heating of the cell, which is again a thermal behavior. Now let's see the cell testing. What are the steps involved in testing a cell? First is the objective. The very important thing is you should know why you are performing a particular test. What will you gain at the end of this test? Then the applications. So once you do the test, what will its results mean to you? Where will you use these results in? Will you use it in designing a BMS? Will you use it in designing a thermal system? Or in what way you will use it? And the test equipments. So obviously when you are performing a test, you should know what appropriate equipments should be used for that particular test. The rating of the equipments should be precisely chosen so that you can perform all the tests. Then test procedure. So each and every test will have a procedure which should be used. You cannot just test with any procedure. There are standard procedures which must be followed, because a cell can behave differently when you follow a procedure in a different manner. So care must be taken that proper procedures are followed. The next important is test duration. As we have saw in different types of tests, some tests like EIS can take a few seconds to a few minutes, whereas some tests like the aging test can take months to years also to actually perform on the cell. Next, the data analysis. So when you do the cell testing in lab environment, it generates a huge amount of data. So data should be properly analyzed and post processed, because this contains a huge amount of information. So if we say the life cycle testing, you cannot wait for 1 year to get the expected life expectancy of the cell. So the initial cycles of data can say you a lot of things. So you can do some data analysis part on that and try to predict what will be the life cycles the cell will give from this initial cycles. Next is the standards. So there are various standards which you will see, which have been set up for cell testings. So these all things should be followed when you are doing any cell tests. Any doubts still here? Okay. So now next we will see few of the tests in detail. We cannot go through all the tests, so we will mostly see the basic tests which are done for the cell. First is the capacity test. So the primary intention of this test is to obtain the energy content as a function of C rate and temperature. So when we saw the data sheet of the cell which says 2600 mAh, but it specifies the C rate and also the temperature. But you may not use the cell at that particular C rate. Your application may need a 0.5 cc and temperatures like Indian conditions may be like 35 degrees Celsius and all. So this test will help you to know how much capacity the cell can deliver or take in at particular temperature. The next is the application. Where will you use this capacity test? As we have seen, this can be used in a vehicle, or if you are using a battery in a vehicle or any other application, then you can use this test to know its capacity at that point of time and at different temperatures. Then the test equipments. So you need a cell tester. So cell tester is a equipment which can charge and discharge the cell at various profiles. You will have a GUI which can help you to set up the tests, and the test will be performed. The tests go on for it is continuous testing. Then temperature chambers. So obviously when you want to know the capacity or capacity at a certain temperature, you should have a proper thermal chamber which can help you to regulate the ambient temperature of the cell. Then the heat camera. Heat cameras are optional, which can help you to study the thermal behavior of the cell. You can see the hot spots in a cell. And the test procedure. In this test, we apply different currents at different temperatures of interest, right? But there are some standards which will say you that when you are finding the capacity of a battery pack, you should use a particular temperature and a particular C rate. For example, many standards say that when you do a capacity test for any cell or battery pack, use temperature of 25 degrees Celsius and C rate of C by 3, this standard practice. So if you use this particular C rate and temperature, then irrespective of what time you are measuring the capacity, you should get the similar time. You should get the similar capacity. Yeah. So let's see what are the different control parameters which you will be setting while doing this capacity test. First is the charging current. So charging current is the CC current. So this is the value, IC value. So charging current, what we saw, C by 3. So this is the current which will be specifying. The next is the charging voltage. So charging voltage means the maximum voltage of the cell in CV phase. So when you stop CC phase, the current reaches the maximum voltage, and when the taper current starts down, the voltage is kept constant. So charging voltage would mean the maximum charging voltage in CV phase. Then next is the charge cutoff current. So here we have used CC CV charging. So once you reach the constant voltage phase, the current will slowly start to taper down. So this can taper for infinite time. It can go on becoming slow. So you should know where do you cut off this current, right? For most electric vehicles, the cutoff is set at around C by 10 value. So whenever the voltage reaches the maximum voltage and current reaches say C by 10, it would mean the charging is complete, 100% SOC. For capacity test, mostly the cutoff will be kept little bit lower, around C by 25 or C by 20, again depending on which standard you are following. Then next is the discharge current. So after this charging, we'll have a discharging phase in which you discharge the cell at a particular C rate. So in capacity test, the capacity which you take is actually in the discharge capacity. The discharge is done at constant current discharge up till the lower cutoff value. And next, the rest time. So this rest time is the rest time between your charging and discharging. So when you do capacity test, you first charge the battery and then discharge it. So how much time do you wait in between charging and discharging? And last is the ambient temperature. So this temperature is the temperature at which the cell is kept. So you should ensure that the cell is, before you start the test, the cell has been soaked in the temperature for about 2 hours or so that the cell is actually at the temperature or the test temperature. Then this figure shows you how the capacity degrades with cycle number. If you want to know the capacity fading of a cell, then you perform this capacity test at various cycles. So this is the first cycle, okay. So this is the constant current, constant voltage phase, and this has been done for multiple cycles. So for 0th cycle, then 200, 400, 600. For 600 cycle, you can see there is short CC phase and long CV phase. So this essentially means the cell has degraded. So this gives you the state of health of the cell. And when you perform this capacity test at a particular C rate and at particular temperatures, then you can arrive at curves like this. So this will give information about the amount of degradation that has happened, because it's very difficult to know the state of health for any battery packs. So capacity test is a standard test followed to see the capacity fading. The next test is the OCV versus SOC. OCV is the open circuit voltage, SOC is the state of charge. The objective of this test is to know what is the open circuit voltage relation with the state of charge at different temperatures. This test is very important test because it helps in the SOC estimation. SOC estimation, SOC is the state of charge which you see on your mobile phones or electric vehicles, and estimating SOC is really very important. Again, the test equipments required are the same: the test chambers, the temperature chambers, cell testers, and temperature sensors. And the test procedure for this is a bit different. So charging may again be CCCV, but the CC current phase is, in CC current phase, the current which we use is very small current. It like C by 25 or maybe also C by 100. This is because open circuit voltage would mean the cell is open circuited, which means no current should flow in the cell, but ideally it is not possible to take the relation then. So we apply such a small current that the II drop can be essentially neglected, and we can assume the cell to be in open circuit condition. So very small current in the CC phase of C by 25 or below is used, and the cutoff can be at much below rate. When you do this test at different temperatures, what you get is curves like this. So this figure shows you the OCV versus SOC relation for different cells. So make 1, make 2 is set for cells of make 1, cell of make 2, and so on. So if you see, each and every cell gives you a different characteristics. The cell which is marked yellow, if you see at 3.8 volts, it is having about 40% of state of charge, whereas the cell in green at 3.8 volts has around 70% of state of charge. So what it means is, given any cell to you, a lithium ion cell of some chemistry, and given its voltage, you cannot directly tell what is its state of charge. You should first know how the relation goes, right. So this curve depends on the cell chemistry. So these curves shown are for NMC, LMO mixed chemistries. If you see LFP chemistry, LFP is a very flat chemistry. The curve goes like, it starts at around 2.4 volts, it will be very flat at around 3.2, 3.3 volts, and then jump at 3.65 volts. That is for LFP chemistries. Then cell make, NMC cell made by company A will not show the same trend as NMC cell made by company B. So even the same chemistry cells made by different companies will have different OCV curves. Then again, temperature dependence. So these curves also show dependence with temperature. At 25 degrees you may get a curve like this, at 35 the curve may just shifted slightly above, and 45 also it may be shifted a bit above. So with temperature also you should know the dependence. And then state of health. The curve for some cells also depend on the state of health. For some it does not, while for some it does depend. So why is this very important? Because to know the range of a vehicle, suppose you have driven up to about 80% of your charge and last 20% is left. So you should know how much more distance can I go. So if a meter tells you that you can go for 10 kilometers, then you should go at least 10 kilometers with that. If your vehicle stops before that, it is a big problem. So estimation is very important. Then is the internal resistance measurement. So the IR measurement, yeah, the objective is to find the internal resistance offered by the cell. The application of this is to find the peak power capability of the cell, because power is limited by your resistance. Then when you are designing the thermal measurement system, you should know how much heat will the system generate. For that again you will need the Joule heating component, which comes by the internal resistance of the cell plus the bus bar and other things. Then also helpful in cell modeling for state of charge and state of health estimations. And test equipment required will be the same, the cell testers and the temperature control chambers. And in procedure you apply a DC current pulse in this. You apply DC current pulse. So you first bring the cell at whatever SOC you want, then next you apply a DC current pulse here. Once you apply DC pulse, the voltage will dip and the discharge will keep on happening for few seconds. Then when you release the current here, the voltage will go up and again settle down. So by knowing the difference in these two voltages and the current which has been passed, you can compute the resistance of the cell. And the resistance offered by the cell is different, again at different temperatures and at different state of charge also. And it is also different at different points in life of the cell. So it varies with also state of health. So it's function of your temperature, state of charge and state of health, all the parameters. So this curve shows its dependence on state of charge and state of health. So this experiment is carried on for a cell. The first set of values are taken at 900th cycle when the cell is being cycled, and it goes on to 1450 cycles, and this is the state of charge relation. So if you see at 900th cycle, this is the variation, the blue curve. So at 0% SOC you can see the resistance is higher, it goes on decreasing till 80% and again little bit shoots up till 100%. But as cell goes on aging, you see this curve goes on shifting up. So resistance actually goes on increasing with the age, and at around 1450 cycles there is this big increase in the resistance. So this is called power fading of the cell. So cell doesn't only lose the capacity but also loses the ability to deliver some power. And again, so this would mean that at the end of the life the battery pack will generate more heat for the same amount of current, and also it cannot give you huge amount of current. So all this data has to go in your designing your battery management system for thermal management system as well as the BMS for state of health computation and state of charge computations. Any doubts still here?
What is EIS test?
Yeah, EIS is electrochemical impedance spectroscopy. So in this test you run, so if your cell is at say 3.6 volts, so the equipment applies same 3.6 volts to the cell, and on top of that it will apply a sinusoidal current pulse, a very small current, and this current pulse will be at different frequencies. So it will be swept, it will go from 1 kilohertz down to 1 millihertz. Then you will see the response at each and every frequency, how the cell responds. Cell will have capacitive component, inductive component, resistive component. So when you sweep this frequency, you will get the Nyquist curve for the particular cell. Using this Nyquist curve, you can derive the RNC components. So from there you model the cell as a resistor, then a capacitor, RC network. So that is mostly used for your cell modeling, electrical equivalent of cell.
For this cell capacity test, how does the rest time affect the aging of it. The rest time
It
between charging and
doesn't,
discharge.
rest time doesn't affect the aging of it, but it affects, see what happens is if you are doing say fast charging, you have done your charging, and after the charging you cannot directly do discharging, because after charging cell will be at higher temperature. You should have a rest period so that the cell cools down to ambient temperature and then do discharge. But if you are done a very slow rate chargings, then it doesn't much matter because cell is still at the same temperatures.
So you said that with the degradation of cell, the CC and CV values will change. Like CC value will decrease and CV value will increase.
Yeah. So with aging, CC value will not decrease, but the CC time will decrease. How much time the cell spends in CC phase, that will decrease. So it means that today your cell phone is new, you put it for charging, you will see that after 20 minutes or 30 minutes it has reached 80% of charge, and then it will start to slow down, slowly it will start to charge. But when it goes to its end of life, that may be different. The time spent will be different in that phase.
But how will that vary? Because it will be a function of the charger. No?
No, so capacitors would mean same current is applied. So in this you are applying a standard same current. So that's why when you do capacity test, you have to follow a standard procedure which will say that always apply C/3 of charge. Okay. So only when you follow certain procedures, then you will get proper results. So if today you are doing capacity test at C/3 rate and tomorrow you do at C rate, you will not get the proper results.